Hey everyone, welcome back. Let's dive right into Chapter 2 of our material with this explainer on the mechanical properties of fluids. Today, we're going to uncover the hidden rules governing the liquids and gases all around us. It's an absolutely fascinating topic that bridges the gap between abstract physics and the very real world we interact with every single day. But before we get into the heavy physics, think about this. You know that physical sensation you get when you dive to the bottom of the deep end in a swimming pool? Your ears kind of pop, or you feel this squeezing sensation all over. Why exactly does that happen? Well, that physical feeling perfectly sets up our journey today because that sensation is a direct result of the mechanical properties we're about to explore. So here is our roadmap for today's explainer. Section 1, what are fluids? Section 2, solids versus fluids. Section 3, the ideal fluid. Section 4, pressure at rest. Section 5, fluid flow types. And finally, Section 6, viscosity and friction. Let's kick things off with Section 1. What are fluids? Defining the state. Okay, so the crucial point here is that a fluid isn't just, a glass of water. It is actually any phase of matter, liquids, sure, but also gases like the air we breathe, and even plasma, that basically cannot permanently resist being deformed. If a substance can flow, it's a fluid. It just continually yields and changes shape under an external force rather than holding rigid like a rock. Moving right along to Section 2, solids versus fluids, comparing stress response. To really get fluids, think about pushing sideways on a solid block of rubber. That sideways push is called shear stress. The solid block actually fights back against that tangential push by developing a restoring force, meaning it wants to spring back into its original place. But fluids, they just go with the flow. They offer virtually zero resistance to shear forces and simply deform continuously. To picture how an ideal fluid reacts to forces, imagine applying stress to different materials. A solid can totally handle a tangential, sliding pull, but fluids can really only be subjected to normal, compressive stress. A fluid at rest can push straight outward, perpendicularly, against the walls of whatever container it's in, but if you try to slide that top layer sideways, it just slips. There's no resistance. All right, Section 3, the ideal fluid. Let's look at the core assumptions. Now, physicists love to simplify messy reality, which brings us to the concept of the ideal fluid. Keep in mind, this ideal fluid doesn't actually exist anywhere in nature. But this simplified baseline is absolutely vital for us to grasp fluid behavior before we add in all the real-world complications. We assume an ideal fluid is incompressible, meaning its density literally never changes. We assume it's irrotational, so it's perfectly smooth with zero swirling turbulence. We treat it as non-viscous, meaning there's absolutely no internal friction when it moves. And finally, steady flow, where the velocity at any specific point stays perfectly constant over time. That brings us to Section 4, pressure at rest, also known as hydrostatics. Going back to our opening question about swimming underwater, pressure is exactly what you're feeling down there. It's a normal force pressing perpendicularly against the surface area of your body. In physics, pressure is calculated simply as that normal force divided by the area. Because the water is just sitting there at rest, it can't exert any sideways shear forces. It can only push straight inward on your eardrums and your skin. That perfectly perpendicular pushing force, spread over a specific area, is exactly what we call hydrostatic pressure. Let's transition to Section 5, fluid flow types, from streamlined to turbulent. Things get incredibly dynamic when fluids actually start moving. What's really interesting here are these thresholds, specifically a mathematical concept known as Reynolds numbers. Think of these numbers as the ultimate speed limits for smooth fluid flow. When a flow has a Reynolds number below 1,000, it stays perfectly smooth. Every single particle glides in a neat, orderly path, which is what we call streamlined flow. But once that number crosses 2,000, the flow suddenly completely breaks into a messy, swirling, turbulent chaos. And right in that sweet spot between 1,000 and 2,000, it's unstable and constantly shifting back and forth between the two states. And finally, Section 6, viscosity and friction, internal fluid friction. So remember when we said ideal fluids have zero internal friction? Well, real fluids are sticky. Viscosity is simply the internal friction of a fluid. This is exactly why pouring your morning syrup is a much slower process than pouring a quick glass of water. The syrup has high viscosity. Its internal layers physically drag against each other and against the walls of the bottle. Water has low viscosity, so those internal layers glide super easily, pouring freely and quickly. Get this, it is absolutely fascinating to see how temperature completely manipulates this friction. For a gas like air, increasing the temperature from 0 to 40 degrees actually slightly increases its viscosity. But look at water. By heating water from room temperature to a rolling boil at 100 degrees, its coefficient of viscosity massively drops from 1 all the way down to 0.3. The heat essentially loosens the internal bonds, making boiling water significantly less sticky and viscous than cold water. And this elegantly leads us right into Stokes' law, which perfectly summarizes everything we've been talking about regarding internal friction. Stokes' law shows how physical dimensions, like the radius of a falling object, combined with its speed and the fluid's very specific coefficient of viscosity, all mathematically interact to create a dragging force when an object moves through a liquid or gas. It perfectly, mathematically, models the messy reality of fluid friction acting against an object.
So I'll leave you with this final thought to ponder. From the hydrostatic pressure compressing you at the bottom of a pool, to the chaotic, turbulent flow of rivers, to the sticky viscosity of honey, fluids truly govern our world in incredible ways. How do these invisible physical forces continue to shape the engineering and designs around us every single day? I hope this explainer has inspired you to look a little closer at the fascinating physics flowing through your everyday life. Keep learning, keep observing, and I'll catch you next time.